So before I get started, I just want to say I discovered on the radio this morning that apparently there's a 1-minute silence for the Manchester bombings at 2:30. So if you've got your hands up asking Fred questions at 2:30, there's a reason that we're not listening to you for a minute. So there'll be a pause after this talk and before Tobias's. So I'm here to talk about pipeline barriers. My name's Andrew. I'm one of two people, not actually two people, like the bathroom scales might think. And we're going to have a brief word about who we are and what we're talking about. I'm going to talk about what barriers are as a concept, because I'm an old theorist. And then Fred, who actually gets to do programming stuff, will talk about how to do them in Vulkan and give examples of their use. So quick word about who we are. We are the ecosystem team in Samsung, or at least we are some of the ecosystem team. We work with a load of software vendors, some of whom you may recognize. And what we do is to try to make Samsung phones look good, and one way we do that is to try to promote people using Vulkan on Android. That means that we go out, work with game studios, try to help them. If you're trying to get stuff to work properly on a Samsung device and having trouble, please get in touch with us. We don't promise that if you ask all of your friends to pretend they're developers, then we'll give them free phones, but you can try it. And Fred gets sent out around the world to try to help people. And there are more people than just him, but he's very good. I, however, am from the team that works on standards and the Vulkan spec. So this is all going to be about how GPUs theoretically do things, and all the hardware vendors here can laugh about how different this is from what they actually do, but somebody else will probably do it that weirdly. So it will surprise you to know that GPUs are parallel things. It's a well-known statement that computer graphics is embarrassingly parallel. What do we mean by embarrassingly parallel? Well, Wikipedia, which is always right, says in parallel computing, an embarrassingly parallel workload or problem is one where little or no effort is needed to split the problem into a number of parallel tasks. Citation needed. Obviously, if there was little or no effort needed, then you could all ignore me and everybody would be much happier for the next 20 minutes. But actually, it's not quite that simple, and even with a highly parallel computer or highly parallel GPU, then there's still some scalar stuff that you have to worry about. So what are we talking about with a parallelism? Well, determining which pixels are covered by a triangle happens in parallel, usually more than 4, but I'm trying to do simple diagrams here. The shading happens in parallel. What's happening with memory happens in parallel. So there are multiple buffers and caches normally used in order to keep a GPU running quickly, and they all have separate memory transfer going on to them. So in summary, all GPUs are parallel. Now, obviously, mobile GPUs aren't as parallel as the enormous lumps of silicon that you have on a desktop with a fan connected to it, but they are still very parallel devices these days. They're not just parallel, they're also hyperthreaded. And the reason for that is to try to deal with the memory access, which is a slow thing. So, for example, you may have some threads running on the GPU, each being responsible for writing to a particular pixel, and they will create coordinates that need to go off to the texture unit, and the texture unit will eventually return a sampled value, and that can get written out to the frame buffer, and all of this takes some time. And it's not just textures, this also applies to accessing the frame buffer, it applies to vertex buffers. There's a lot of latency there. And having all of these threads allows the GPU to hide things. But it does mean that there's more going on than you might expect. So the ALU is also pipelined. Every modern CPU is pipelined as well. But it's the memory that's the complicated thing that can take tens of cycles. So if you're looking at a mobile GPU and saying, oh, it's not that parallel really, actually the number of threads you have running can be really high. And you may have met the graphics pipeline before. I don't know if anybody's ever taught you this. But it's often the case that a university professor may say, oh, look, here's some vertices they'll go through, they'll turn into a triangle, they'll get rasterized, and so on. And you get this impression of one thing passing through the pipeline. And of course, it is a parallel pipeline. There's stuff going on in all of these stages. And in order to keep the flow going on, you need to have extra buffering happening between the stages, and on top of that, multiple things are being processed from those buffers in each stage at the same time. So in particular, if you have a load of shading happening on triangles, all of which are writing to one fragment, they may not finish shading in the order that you're expecting them to, because there's a load of stuff happening in parallel. Tiled GPUs, hopefully if you're here you know what a tiled GPU is, can be even more explicitly pipelined. So if you don't know what a tiled GPU is, ask the ARM people, but tiled GPUs do all of the rasterizing within one tile independently of what's going on in the other tiles. So particularly that means that if you're dealing with a primitive in one tile and you finish shading it and then you're working on the next primitive and so on, all of those may happen before the first primitive gets touched at all in one of the later tiles. And on some GPUs in particular, the tiling stage and the vertex processing stage can happen so separately from the fragment shading that they're actually in different frames. And that's done for optimization reasons that are very good, but it does mean that everything doesn't immediately get shoved in one end and fall out the other very efficiently. It may not be obvious, but vertex shaders can often get run more than once. Now, this can also happen on desktop if your vertex cache is missing. But particularly in this case, you may find that during tile rasterization, the vertex shaders get run more than once. So where I'm going with all of this is when you go to your tool vendor and say, I want to know how many cycles my shader took to run, because I want to optimize my game, do you mean the difference between when you started it running and when it finished running, the number of cycles it was running in total, which time it ran, and so on. So it's all very complicated. And the memory, as I was saying before, is accessed in parallel as well. So GPUs require caches to get good performance. And if you don't believe that, you may think DRAM's got really fast these days, and in terms of bandwidth, it has. But if we go back to 1995, which is so long ago, I'd only just graduated, then it took you 20 nanoseconds-ish to do a completely random access to some memory. And now we can do it in 8 nanoseconds. So that's 2.5 times faster in 23 years. So eat that, Moore's law. So we rely on the caches to be able to access stuff quickly. So in order to make those caches work efficiently, they're often special purpose. So the texture cache may be special, the frame buffer may be special, and these things don't necessarily snoop each other. So you can't rely on data transferring from one to the other efficiently unless you're doing something explicit to say it needs to happen. On top of that, so you may know if you're storing an image in memory, traditionally you just do it in raster order. There's a 64 by 64 doodle I drew on the back of a bus. And each of those lines takes up 64 pixels, and that might correspond to a cache line, for example. And if we then try to rasterize a triangle that needs to read the data out of that texture, then we find it crosses quite a lot of those lines. And that's not necessarily very efficient. So particularly a problem is that if you're sampling, you're accessing more than one line at a time, and the order in which you're processing pixels on while you're rasterizing that triangle may not line up neatly to where that data lies in the texture cache. So what can we do about that? Well, you can break everything up into tiles. Tiles are wonderful. So if you instead arranged your 64 pixels into 8 by 8 blocks, then you find that you access much fewer of those while trying to rasterize the same triangle. Everything gets cached more efficiently and more easy. I've shown 8 by 8 tiles. Of course, there's no particular reason it could be done like that. Each GPU has its own way of doing these things, and that's not to say that the order of pixels within the tile is linear. That's not to say that the order that the tiles are stored in memory is linear. All of this is proprietary. There's also, in addition to the tiled layout, there is a different kind of layout, and this is what Vulkan calls layout. And that's different memory representations that can allow things like compression. So for example, you might have lossless compression dealing with your frame buffer. You might have efficient ways of dealing with multi-sample, so that if all of your multiple samples are shaded to the same value, you don't end up writing them all out to memory. You may end up with hierarchical depth buffers. All of these are ways of reducing bandwidth and improving cache behavior. But all of them have different ways of laying stuff out in memory. And so the GPU needs to know what you're doing with a block of memory in order to do this. And that representation, while it's generally speaking lossless, it's only lossless if you give it something that makes sense to process. So if you start writing random data into your texture and try to pull it out, and it's floating point texture, don't necessarily expect all the nans to stay the same as they started, for example. This isn't the same thing as the lossy texture compression that we might be encouraging you to use to reduce bandwidth. That's visible to the end user, but the layout is how the GPU more efficiently accesses memory. And because the GPU needs to know what kind of memory it's dealing with and what you're trying to do with it, that's one of the uses of barriers. You can indicate the transition point between two different layouts and two different uses of a block of memory. The CPU has to see the memory as well, and that can't have this proprietary view because you need to know what you're looking at. And the GPU vendors generally can't expose all of their dirty laundry on how this stuff is laid out, because then they wouldn't be able to update their designs very easily. Desktop guys do have some layouts that are standardized, but that's not currently the case in mobile. So if you're going to access stuff from the CPU side, you still need a standard, simple layout, but that's not an efficient thing for the GPU to be using most of the time, so you need to handle transitions between them. So if you have a load of triangles that are being processed in parallel on fragment shaders, all writing to the same pixel in the frame buffer, then there's this parallel complexity. And if you're just rasterizing something to a frame buffer, then you want everything to be handled simply. So you don't really want to have to insert a load of synchronization operations. So game developers would get mad if you had to do that, or be mad, or one or the other. In fact, I've met game developers, they are already mad. But the good news is that the silicon vendors have decided to pull their hair out to make this problem work. And I know silicon vendors with lots of missing hair, so that explains one of the reasons why. So if you're just doing simple rasterization, as was taught in the early versions of the GL Redbook, then everything happens as if it was in order. And the thing that sorts out the mess is usually the blend unit, but basically some magic hardware in there will make everything work for you in the simple case. And that applies for as long as you're just writing data into the frame buffer. As with all computer graphics, you can do all kinds of cheating stuff behind the hardware in your algorithms, and as long as nobody notices, everything is fair game. Just don't get caught. But the problem with magic is it doesn't exist. So although we can deal with the cases where you're writing to a frame buffer and you need to worry about write ordering, if you wanted to be able to get at the frame buffer data, for example, then you've got two different blocks of memory to worry about. So the GPU can handle the most common case for you, but it can't handle everything you might do to have incoherent accesses. The older APIs tried to do some clever things to make things work as you might expect, but without you having to do anything clever. And the problem with them doing that is that they had to be conservative to make everything work, according to the mental model of how a simple GPU existed. And in order to do that kind of thing, they sometimes got it wrong. There were overheads that are inserted in making everything look synchronized. And when they get it wrong, your code goes slowly. So that's one of the intentions of modern, more explicit APIs, is to be able to say explicitly when you need this kind of thing to happen. So as examples of that, if you're trying to read the frame buffer during rendering, so you're writing out to the frame buffer during rasterization, you're then trying to read that data back in and pull it from your fragment shaders. That doesn't work as well as you might hope. It certainly would require for the fragment shaders to work in a particular order, and we've already said they're working out of order. The representation of the frame buffer may not be what the texture cache is expecting. So basically, this doesn't just magically work for you. In fact, that's true of writing outside the frame buffer in any kind of shader. For example, if you've got vertex shaders that are writing out intermediate values, if you write to one location, you'll get them in a fairly random order because the vertex shaders will run in different orders on different hardware. And for tilers, the situation is particularly complicated because this frame buffer is living in tiled memory. And if you're trying to access anything other than the current pixel, then you have to worry about what order your tiles are processing stuff in as well. So trying to access anything that's not local is particularly complicated. Quick word about GPU compute, which is not so much my area. But back in around 2001, there were a load of SIGGRAPH papers saying, did you know you can do compute using GPUs because they're these parallel things? And then people started to encourage it by having compute APIs. The good news is they give you more explicit control over the memory that you're reading and writing, and the order in which things execute. But the onus is completely on you to deal with the synchronization. And so you need the primitives that we're about to talk about here to deal with the order in which processing happens. So what can you do to try to make things efficient? So if you're reading data from the pixel that you've just written to within a tile, so Vulkan has the concept of a frame buffer local dependency. There is an ordering of operations. You need to make sure that you've got data in the frame buffer that you're then pulling out, but that only needs to happen inside the current pixel that's being processed. And that's particularly important for tilers. So if you're doing arbitrary access to the frame buffer, and you need to be able to access anywhere within it, then the first subpass of work that you're doing needs to finish completely. All of its data needs to get written out to memory, and then the second subpass can read everything back in again. But all of that memory transfer and synchronization overhead is slow. On the other hand, if you know that you're only accessing the current pixel, then because both of these can run while a single tile is being processed, then everything can work much more quickly. That's particularly efficient on a tiled GPU. So if you're doing local dependencies, it's tile local, and we've given previous talks on how much memory bandwidth you can save by doing that kind of thing. So is this completely theoretical? Not really. Wow, that rendered fast. So a typical way you might want to do this is for deferred shading or deferred lighting. If you do some rasterizing into the frame buffer and then pull the data back out again to look at what ended up in your current pixel and then do lighting operations on it. That kind of thing can work really efficiently in a tiler, but you need to tell the API that the only thing you're going to access is the local pixel. That's a bit of a lie, but so long as you're setting up your subpass configuration inside Vulkan, then all of these dependencies are relatively simple to deal with. You don't need to have explicit synchronization primitives dealing with each tile talking to each other tile, for example. That kind of mechanism is efficient, and particularly compared to writing everything out to memory and then pulling it back again, it's much more efficient in terms of memory transfer. That's true for tilers, but it's not really true for immediate mode renderers. So if you're doing all of your application development on a desktop machine and your rendering mechanism involved you writing everything out to the frame buffer and pulling it back, it looked like it went fast. And then you'll port to mobile and you'll wonder why everything runs extremely slowly. That might be why. So this really does matter in mobile. In fact, it matters so much, that's why subpassers were put into Vulkan. The only caveat to that is that it does only work for accessing the local pixel, so that everything can stay within the tile. So if you're doing some kind of post-processing effect that involves you doing lens flare or motion blur or something like that, and you already needed to access surrounding pixels, bear in mind this mechanism won't of itself work for you. So what do we do if we want more global synchronization mechanisms? So there are barriers. Barriers stop things. And particularly, you might, in this case, have some rendering happening where you want to access the result of some previous rendering inside a texturing unit. So here is a subset of the graphics pipeline. And we can have the second block of work running, and it needs to be able to access the result of the first block of rendering by the time the fragment shader is running in order to be able to texture from it. So these do happen on a pipeline stage by pipeline stage basis, so you can specify where the barrier is working, and it's important that you only block where you want to block. So remember what I was saying, that on many tilers the binning pass happens in a different frame from the rasterization, and particularly this can be happening while all of this rendering is going on. And particularly it can overlap with the fragment shading of the first workload. So if you didn't start this vertex shading work until after you'd finished rasterizing the first block, then a load of parallelism would have gone out of the window. So block only on the stages that you need. You can have frame buffer local dependencies in barriers. Most of the times I can think of for doing that, you probably wanted to use a subpass instead, but the concept does exist. But they're more useful for global dependencies. So for example, as in this case, if you did a load of rasterizing to produce a shadow map, and then you're trying to access the shadow map inside your fragment shader for the second pass, then that can work relatively efficiently and use a barrier to make sure that everything is finished rendering into the shadow map before you try to access it. And if you're doing compute kind of stuff, then this is a very sensible way of trying to do synchronization for compute. The only problem with them is that we've said that GPUs are parallel and we want to keep them parallel. If we're making the pipeline block at a given point, then that's removing parallelism. Everything is stopping. So there are also events in APIs like Vulkan. Because we don't want to stall everything, and we do want to keep things going in parallel, what we would like is to have a way of having this work running while we're potentially doing the wait between that, the results of the first block of work and the thing that needs it down here. So events let you have multiple dependencies of this type active, and you can think of them as a request that goes into the pipeline and then something that waits for that request to pop out of the pipeline once work has reached a certain stage. So you should only block on work that you actually need to have complete, and you can be having incomplete, unrelated work executing in the meantime. Events are also visible to the application, so you can access them from the CPU side, and that theoretically means you can make the GPU wait on something that the CPU is doing. But bear in mind, if you make the GPU wait for too long, then everything will think it's crashed and the whole system falls down, so don't do that. So, in summary, GPUs are parallel, who knew? And they're not that fast if they're not parallel devices, so do keep everything going in parallel, but that means you have to worry about synchronization. Only the real basic stuff happens for you automatically, and the most basic stuff means rendering to a frame buffer, everything will pop out in the right order. If you're doing something more complicated than that, then you need to pay attention to these primitives. So what do you use? Use subpass dependencies if you're doing local access to a particular pixel. You can use pipeline barriers for pretty much everything else, but if you want to keep work flowing through the GPU and keep the pipeline busy, then you can use events to allow multiple things to be queued up at once. This is a massive simplification. The way that GPUs actually work is much more complicated than this, but this is the simple version that makes sense in an API. So talk to a GPU architect if you want the full horror. So that's the end of my bit. That's all theoretical. And now we get to the bit where you have to program it. So I'm going to hand you over to Fred, who actually knows about programming. Right.
Sure. Hello everyone, can you hear me? Cool, all right. So I'm Frederic Garnier, working for the ecosystem team at Samsung UK. And so what I do, as Andrew described, is work with game developers, support their games, fix issues, and try to make sure that their porting experience to Vulkan is the best that they can get. So Andrew's explained how barriers are exposed, well, work in GPUs. Basically, the message is GPUs are very parallel. And Vulkan is an explicit API like D3D12, Metal, and so forth. And the idea with those APIs is to give the developer the ability to take advantage of the GPUs and synchronize your resources accordingly. So as a disclaimer, I want to say that our results and experiences are based on working with the following titles and a few more. So Axe by Nexon, Final Fantasy 15 by Square Enix, Lineage 2 Revolution by Netmarble, Honor of King, also known as Arena of Valor by Tencent, Blade 2 by Action Square, and Protostar by Epic Games. So that's based on us and the game developers working with the Galaxy S7, S9 devices using the ARM, Mali, and Qualcomm GPUs. So as I explained, in Vulkan, it's a very explicit API, so all the resources that you've got during the lifetime of your frame have to be tracked. So you have to make sure that they're in the right state. That includes layouts and all sorts of things. So layout is what Andrew described earlier. The other thing you need to take into account is, are you reading and writing to the resource in the correct order? And are you also executing operations in the right order? So by operations, I mean, for example, I'll have an example afterwards. But basically, if you're doing a copy and sampling data from that image where the data's been copied to, are you sampling that image in the right order? As in, are you sure that the copy is complete before sampling? So in Vulkan, being able to inject pipeline barriers into the command buffer is done with this call. So the relevant flags here are source stage mask and destination stage mask. And they're shown on the right-hand side here. So source stage mask can be thought of as the producer, and destination stage mask can be thought as the consumer. So the idea is you wait for the source stage to complete, and once that completes, then you unblock the stage and destination stage mask. So the relevant flags I'll show today are fragment shader bits, which is, so it's basically the fragment shader, where you're shading fragments. Color attachment output bits is where where you're writing to the frame buffer. Transfer bit is where copies happen. The other very relevant flag is dependency by region, and Andrew mentioned that in the context of subpasses, where essentially if you have multipass, so Hans Christian talked about that last year, if you have multipass and several subpasses, if you're reading from the previous pixel, then you don't want to wait for the entire subpass to complete, as in you don't want the dependency to be frame buffer global, but rather you want the dependency to be frame buffer local, since you're only reading the previous pixel. The other important bit is the memory barriers, so that there are 3 parameters in a call to vgit command pipeline barrier. There's the P memory barriers, which is basically used for global memory barriers. Buffer memory barriers, which essentially enables you to tell the implementation to synchronize against a specific offset within a buffer. And then image barriers can be used to perform layout transitions as well. So you can see there on the right-hand side, I've only shown the one specific to image memory barriers, since that's what I'll focus on. And I'll talk about the relevant flags right after that. So access masks, those define the type of access you're doing in a specific, in a stage. So source access mask basically means the type of access you're doing in the source stage. And destination access mask is the type of access you're doing in the destination stage. So the green ones there are the relevant ones that I'll talk about today. Shader reads is basically reading data from the shader, vertex or fragment or whatever. Color attachment reads, color attachment writes is reading data from the frame buffer or writing to it, and transfer write is when you copy data to an image, which is what I'll describe shortly. The image layouts, as Andrew describes, it's basically a usage hint to the driver. And the idea is if the driver knows in which layout an image will be in, then it can do some further optimizations. So for example, before presenting the image to the display, you have to transition it using a pipeline barrier to present source KHR, shown in green there. And that basically tells the implementation that the image will be used for presentation. And you also have color attachment optimal, undefined, transfer destination optimal, and pre-initialized. And I'll go through some of them right after that. So images in Vulkan are created with a tiling arrangement. So I had specific tiling arrangement written there before, but that's not really correct. So you've got linear tiling, which basically means row major order, and you probably have some padding there as well. And the other flag that's exposed in Vulkan is known as optimal, aka swizzle tiling. And what this means is that the image is laid out in a GPU-dependent arrangement, which can be more efficient for specific use cases. So for example, by linear filtering, it can be laid out in a specific way, which makes it more efficient for 2D access. Images that are created with an optimal tiling arrangement require an explicit copy, since you're actually copying the data from either a buffer, which is in a linear arrangement, or an image in a linear arrangement to optimal. So it's possible to avoid that copy if you're using linear, and that can be useful in some cases where you're dynamically updating the image every frame or something. But the downside is if you're using an image with linear tiling, then you're losing out on performance. There's no support for bitmaps. And the other thing is, in terms of formats, there are a lot of limitations. So you've got to make sure that your GPU supports what you want to do if you're using linear tiling. So generally, we recommend to go with optimal. So in my example, it'll be a very simple one since pipeline barriers are already overcomplicated. Basically, what I'll describe is copying data to an image in optimal tiling. And that will be from a buffer or an image in linear tiling that has the data that's been copied to by the host. And then basically making sure that we synchronize correctly so that the copy happens, the sampling happens in the right order. So you can see there that the sampling operation has a dependency on the copy operation because we want to wait for it to complete. So the way we can do it, and that's the pipeline barrier we need for the copy, is basically to specify that our source stage will be top of pipe. And the reason it's that is because we don't need to wait for anything to complete. So our image in the optimal tiling has garbage data, and we can issue the copy right away. We don't need to wait for anything before doing that. Once that's done, which will be right away, then the transfer stage gets unblocked. We also specify the type of access we're doing in the top of pipe bit stage. So that stage, just like bottom, doesn't access memory. So we just specify 0. In the copy, we're doing a write, since we're copying data to the image. So we specify transfer write. We also have to make sure that the access that we're specifying matches the stages. So that's specified in the Vulkan spec. You can only use specific accesses based on the source stage mask that's been specified. And the other thing is image layouts. So undefined basically means that when you're transitioning from that layout to another one, you're basically telling the driver / implementation that you can discard the data. So we're transitioning to transfer destination optimal, which is the layout you need when you're copying data to an image. And then for the barrier right before sampling, to make sure that the copy completes, we specify transfer stage as the source stage because we want to wait for that to complete. And once that completes, then we unblock the fragment stage where the sampling will happen. So we were doing a transfer write, and we'll be doing a shader reads, so sampling from the image. And in this case, we can't specify undefined as the layout since we'll be discarding the data. So we specify the old layout and transition to the new one. Another thing that's very important, and actually a few weeks ago I was chatting with my manager, Richard Huddy, who was telling me that back at his AMD days, one of his key words was always batch, batch, batch. And that actually took him pretty far, as he told me. So it doesn't just apply to pipeline barriers, but it also applies to draw calls and every single thing that you're doing in the API. So if you can reduce the amount of draw calls you're doing, or the amount of pipeline barriers you're issuing, by batching, then you should do that. Because the issue with all of those calls is it has an associated CPU cost to it, which can reduce performance. So generally what we do when we support game developers is capture a trace using a tool and look for how many pipeline barriers are being used within a frame. So generally we look for if there's 20 plus, then we'll go through it and see whether they're redundant or they can be batched. And if we can batch them, then we will. Subpass dependencies, Andrew mentioned that. So basically in Vulkan, you've got the concept of a render pass. And within a render pass, you can have multiple subpasses. And a render pass enables you to specify a layout for each subpass, and at the same time specify a final layout that the image gets transitioned to at the end. Generally, subpass dependencies can be more efficient than using a pipeline barrier. So in the case of rendering and presenting. And the reason we didn't use that before is because functions in Vulkan have a render pass scope, which means that they can either be used inside a render pass instance, so between begin render pass and then render pass calls, or only outside of a render pass instance. So in the case of a copy, like vk command copy image or vk command copy buffer to image, you can only use that outside of a render pass instance, which means you need to use explicit pipeline barrier calls. Subpass dependencies are slightly more complicated in the sense that you've got a lot of structures that you need to fill in. So one structure I didn't show here is vk subpass description, which is a description for a subpass within a render pass. And in that structure, you're basically referencing an attachment, and that's shown there as VK attachment reference. In that structure, you basically add your index, the index into the attachment, and the layout that this image will get transitioned to in the relevant subpass. In VK attachment description, you specify the initial layout, which is the layout before the render pass, and the final layout, as in the layout the image gets transitioned to after the render pass ends. The most relevant structure here is VK subpass dependency. So the flags are similar to what I showed before with the pipeline barrier call. So source subpass and destination subpass specify the subpasses you're synchronizing against. Stage masks are similar to the pipeline barriers. Same goes with access mask. And dependency flags basically enables you to specify that the synchronization will be frame buffer local if you have multiple subpasses, so that you don't have to wait for the entire subpass to complete if you're reading data from the previous one. So my example going through subpasses will be a very simple one, basically just based on rendering a triangle or rendering whatever, and then presenting that using the WSI extensions. So there won't be any code samples, but it's just so that you have a general idea of what I'm trying to explain there. So while you can specify the layouts in a subpass for each subpass and specify the final layout, and then that gets transitioned to automatically, it can still happen out of order. So you've got to make sure that you're doing it right. In this case, you've got to make sure that the presentation engine is done reading from the image, and the subpass dependencies and other external dependencies like semaphores, which I'll explain later on, help us make sure that this is happening in the right order. So to transition the image when it can be rendered to, in the case I explained before, we rely on the acquire semaphore, which we use when we're submitting a batch to the GPU. As part of the acquire semaphore, so there's a structure called VK submit info. You specify the stage where the semaphore wait will happen. And basically, this execution dependency helps us only with the execution, and the subpass dependency basically makes sure that the layout transition happens at the right time. So it happens when you can actually render to the image. Subpass dependencies are not just limited to presentation, but actually can be used for off-screen rendering, deferred shading, all sorts of things. As you may see on the Vulkan spec, there is an implicit subpass dependency that's automatically applied, and that's known as a pre-dependency. So it's basically the dependency that is applied automatically for when you're transitioning from the initial layout before the render pass to the layouts as the subpass begins. So the stage it specifies is top of pipe, which basically means transition right now, which you don't want to do since you want to transition when the semaphore gets signals. So ideally, you'll specify a stage. So basically, you're waiting for the color writing stage to get unblocked, which is where you can actually render to it. And then once that happens, then the layout transition can occur. We also specify the relevant access. So I've highlighted read bits in orange because in this example, we don't actually need to read the image. We're not doing any blending. We're just writing to it. So in that case, we could just use write bits, but it's very common to use both. And then to transition to the presentable layouts at the end of the render pass, we also need another subpass dependency. There is an implicit subpass dependency which exists, which is also fine since we have a graphic semaphore that gets signaled when work is done, so at bottom of pipe. We don't need to explicitly define this subpass dependency because the transition will get done at the right time, but we can still do that. So the post dependency that's injected automatically is defined like so, which is fine, as I said, since basically the stage that gets unblocked is bottom of pipe. But we can still change it to this if we want to and specify the relevant access masks, stage masks, whatever you want. And then as a case study, so we worked on several games looking at what they were doing, and we noticed a lot of issues. So this one is actually based on Lineage 2 Revolution by Netmarble. So what they were doing was they were rendering to an image, and then they wanted to sample that image. they issued a call to VG command pipeline barrier, but they were using the wrong stage masks, which then led to some pipeline bubbles we could see with some tools. So we changed that to color attachment output. So we're waiting for rendering to complete. And then once that completes, we unblock the fragment stage so we can sample the image. Doing that has reduced the pipeline bubbles. I'll show. So that's a DS5 capture, which is based on lineage 2 revolution. So initially, when we profiled the OpenGLES version, which was the original one, we saw a frame time of 20 milliseconds. And then porting that to Vulkan. So by porting, it's not an actual port. The game is based on Unreal Engine 4, so we just used Vulkan. And the original barrier stages were not correct, so basically performance was worse. Optimizing that and batching the calls to command pipeline barriers reduced frame time, which increased performance for us. Along with working on Unreal, we also worked with Unity 3D and optimized some of their games. So some of the games that use Unity have been Final Fantasy 15, which we went to in Japan, Axe by Nexon, so the studio is based in Korea, and Honor of Kings in Chengdu, China. So the original implementation, OpenGLES, based on our capture, was running at 15 milliseconds. Porting that to Vulkan with all graphics bits, so that's the stage masks in the pipeline barriers, faster than OpenGLES, but still not as good. And then optimizing that, batching has reduced frame time even more. And that's Final Fantasy 15, Pocket Edition. So as I explained, we traveled to Okinawa to support Square Enix and Summertime Studio, optimizing their game to reduce frame time as much as possible. The message I want to give away today is that Vulkan's a very complicated API. Synchronization is probably one of the most complicated things. And even for me, I'm still learning more every day. But Vulkan enables you to make sure that you're doing what you want to do as an application developer and not rely on the driver doing it for you behind closed doors. So that's all from me today. And it's 2:27, so there's no pause for now. That's it.